Hello everyone. Today we'll be talking about how to use Ansys Workbench Additive to simulate laser powder bed fusion, which is a specific type of metal additive manufacturing process. Laser powder bed fusion, or LPBF, works by spreading a thin layer of metal powder on a base plate, then using a laser to melt the cross-section of the part to this base plate. The plate is then lowered, a new layer of powder is spread across the surface using a recoater blade, and then the next cross-section is melted, fusing it to the previous layer. This process is then repeated until the final layer is built at the top of the part. This process puts a lot of heat into the part, causing thermal strain and distortion as it cools to room temperature. Simulating this process in Ansys allows us to predict and compensate for this distortion. It also allows us to get other results such as residual stresses, plasticity, and build plate distortion. It can even allow us to predict and prevent build failures that can happen when the powder recoater blade crashes into the part. Next, I'll show you an example of an LPBF model created in Ansys Mechanical. This is a pitch arm from a helicopter rotor head, along with some support structures and a base plate for the additive manufacturing process. The process of setting up this analysis in Mechanical is really easy. We have this LPBF setup wizard, which is essentially a guided workflow that will basically walk you through the process of defining the part geometry, the base plate, the support structures, the mesh settings. It'll set up the contact for you, have you set up material assignments. It also has you defining things like the actual machine parameters, things like hatch spacing, deposition thickness, scan speed, and so on. So you'll just click Next and fill out all of the pages in the setup wizard, and then this will be ready to solve. So let me show you what it looks like on a version that I've already set up and solved. And anything that you set up there in the wizard can also be customized after the fact in the tree here in Mechanical. So you can see in the build settings, in the details here, you can see all of those machine parameters, and those can be changed here. You can also run back through the wizard if you need to. Also, once we have this set up, we can take a look at the additive manufacturing process sequence so we can see what we're simulating. In Workbench Additive, we simulate this process using a one-way coupled transient thermal into static structural analysis. So what that means is that we're simulating the process to calculate the time temperature history in the transient thermal analysis, in this case for the build and cool down steps, and then transferring that whole time temperature history result into our static structural analysis to calculate our thermal strains and all of the resulting structural results that we're interested in. And in the structural analysis, you'll see we're not only simulating the build process and the cool down, we're also going to be simulating cutting off the base plate as well as the support structures to see how that affects our distortion and residual stress results. So here we can take a look at the temperature results from our transient thermal analysis. So you can see we're using a technology called element birth and death to activate entire layers of elements sequentially from the base plate to the top of the part. These elements are activated at the material melt temperature, and that is set as their stress-free reference temperature. And then as the part cools down, it's going to be developing those thermal strains. And those will all be calculated here in our structural analysis. So thermal strain is calculated as alpha times delta T, where alpha is the material's coefficient of thermal expansion, and delta T in this case is the change in temperature from the melt temperature all the way down to room temperature as the part cools. So here's our total deformation plot. We can animate this as well. So you can see the part being built, cooling down, base plate being cut off, and then the support structures being cut off sequentially. So there's our deformation results. These can be used, like I mentioned before, also to compensate for this distortion so that the part is kind of pre-deformed in the opposite direction, and then when it deforms through the manufacturing process, it ends up within spec. We can also look at other results, such as our residual stresses caused by the manufacturing process. So this is how you can use Ansys Workbench Additive to simulate the laser powder bed fusion process. And if you're interested in more information on this or on other types of additive manufacturing processes that Ansys can simulate, please click the link in the description below.